All right, now let's look into the next problem here. Again, on variable separable form. So here we have a question: xy dy by dx is equal to 1 plus y square by 1 plus x square times 1 plus x square. I would request you all to pause the video and try it yourself. All right, now hope all of you have given an honest try to this. So let's discuss this. So xy dy by dx, okay, I can write this as 1 plus y square, okay, and within this I can write it as 1 plus x square plus x divided by 1 plus x square divided by 1 plus x square, okay. So this 1 plus x square by 1 plus x square, you can write it as 1, so it becomes 1 plus x by 1 plus x square. Now let us separate the variables out. So y dy divided by 1 plus y square is nothing but 1 by x plus 1 by 1 plus x square dx. Okay. Now given the variables have been separated, now I can start the process of integration both the sides. So let's integrate both the sides. This will simply become half ln of 1 plus y square. And on the right hand side, you'll have ln x plus tan inverse x plus a c. Okay. Now since there are multiple ln's, you can also write your constant as ln c also, just to facilitate clubbing of the ln terms. So when you do the clubbing of the ln terms, you can write it as ln under root of, you can put an ln on this side also. Okay, you can put an minus ln c. It doesn't matter actually, because minus ln c will also be some other constant. Okay, so you can put minus ln x minus ln c is equal to tan inverse of x. So that is nothing but ln under root of 1 plus y square by cx is equal to tan inverse x. Okay. Finally, simplifying this result, it becomes 1 plus y square is equal to e to the power tan inverse x times cx. So this becomes your answer. Now, many a times I get this question from students: till what stage should we simplify this? See, actually, it depends upon the option given to you in the question. Okay. So whatever options are provided to you, according to that, you have to take your simplification step. So there is no limit, or there is no fixed step where you need to stop it. It is all decided by the options provided to you. Now we'll talk about certain types of differential equations which are not directly variable separable, but they can be reduced to variable separable. So next topic is what we are doing is reducible to variable separable form. Reducible to variable separable form. Okay. Let me illustrate this by a very, very simple example. Let's say I want to solve this differential equation dy by dx is equal to x plus y the whole square, right? Now here you can see that your x and y are so linked that you cannot separate them out completely. Okay. So what I'm going to do here is I'm going to call x plus y as some other variable, let's say v, right? Now, according to this substitution, I have to change the entire differential equation. So as to say that I have to change my dy by dx also in terms of v. So when I differentiate both sides with respect to x, this is what I get to see. In other words, my dy by dx is nothing but dv by dx minus 1. Okay. When you make this substitution over here, when you make this entire substitution over here, your entire problem takes a slightly different form, that is dv by dx minus 1 is equal to v square, right? Which is nothing but dv by dx is equal to 1 plus v square. You can clearly see that it's now a variable separable. So you can write this as dv by 1 plus v square is equal to dx and perform the integration on both the sides, right? We conveniently know the result for these integrals. This is nothing but tan inverse of v, and this is nothing but x plus c. But do not forget to place back your v in terms of x and y. So now this can be written as tan inverse of x plus y is equal to x plus c. You may also write it as x plus y is equal to tan of x plus c. Okay. Again, to what extent we need to simplify it, that is being decided by the options provided to you in the question. All right. Now let's have a look at another example. Now I would request you all to please pause the video at this point of time and give us and try this question on your own. I hope you all have tried this question now. Now let us discuss this. Before we solve this question, we have to make an observation over here that we have a 2x plus 3y term and 4x plus 6y term. We can clearly see that this term is exactly double of this, which actually indicates towards a substitution for you. Okay. Now, many a times people also include the constant. So what we are going to do here is that we are going to take 2x plus 3y minus 1 itself as some other constant. Let me call it as u. Okay. When you do that, please note our expression is going to change accordingly. By the way, our expression is nothing but dy by dx is equal to negative of 2x plus 3y minus 1 divided by 4x plus 6y minus 5. This is our desired given expression to solve in the given question. Correct? Now, after making this substitution, we have to substitute for dy by dx accordingly. So if you differentiate both sides with respect to x, this is what we end up obtaining. Right? So you can say that your dy by dx expression is nothing but du by dx minus 2, 1/3 of it. Correct? If you place this in this given scenario, it becomes 1/3 du by dx minus 2 is equal to negative, this is u, and this term is nothing but 2u. Remember, 2u will give you 4x plus 6y minus 2. Okay, and you need a minus 5 here, so you have to do an additional of minus 3 over here. Correct? Now we'll try to separate the variables in this case. So first let me take the 3 on the other side and add a 2. So du by dx is equal to minus 3u by 2u minus 3. Okay, send this 2 on the other side, which will become a 2. So this will become 4u minus 6 minus 3u divided by 2u minus 3, which is nothing but u minus 6 by 2u minus 3. Okay, separating the variables out, it will become 2u minus 3 by u minus 6 du is equal to dx. Now, a perfect state for us to start integrating both the sides. Now, how do we integrate our left hand side? To integrate our left hand side, we'll try to generate a u minus 6 on the top, which is quite easy. You can do it as 2u minus 6 plus a 9. Right? See, all you are using here is your skills of indefinite integrals, nothing else. So this becomes twice du plus 9 over u minus 6 du is equal to dx. Okay, so that is nothing but 2u plus 9 ln mod u minus 6 is equal to x plus c. Let me place back my u, which was 2x plus 3y minus 1. So 2x plus 3y minus 1 I'm placing in place of u plus 9 times 2x plus 3y, it will become minus 7 is equal to x plus c. Okay, so if you want, you can further simplify this. So 4x here and x over here will give you a 3x. 3x plus 6y minus 2 plus 9 times ln mod 2x plus 3y minus 7 is equal to a constant. This becomes your solution to this differential equation. Okay, So all I've done is through a use of substitution, we have converted it to a variable separable form and tried to solve this question. And therefore this method is called the reducible to variable separable form. All right, let's have a look at yet another problem. Again, pause the video, try to solve it on your own. All right, so hope you have given an honest try to this question. So let's discuss this. So d2y by dx square is equal to dy by dx the whole square. Now, if you see this left-hand side term d2y by dx square, it is nothing but d by dx of dy by dx, correct? So what we can do is we can actually call dy by dx as p. Now, that's actually a norm that we also follow. We normally use the alphabet p to represent dy by dx, okay, especially when there are higher order derivatives involved. So we'll call this as dp by dx, right? Remember, you are differentiating dy by dx again with respect to x, and dy by dx has already been called as the alphabet p here. So dp by dx is nothing but p square, correct? Now you can see that it's clearly a case where your expression has been reduced to a variable separable form. So we can separate the variables out in this case and write it as dp by p square is equal to dx. Okay, let's integrate both sides now. So integration of this becomes minus 1 by p is equal to x plus c. Okay, now we know that p is nothing but negative x plus c, and this term is nothing but your dy by dx term, right? So from here on we can easily proceed because it's just a case of again separating the variables out like this. Okay, so the derivative of this will be y, the derivative of this will be ln of mod x plus c plus another constant. Let me call that constant as ln k. Okay, so you can write this as y is equal to ln of k by x plus c. Okay, you can get rid of your ln by writing it as e to the power y is equal to k by x plus c. Okay, or you can make y the subject of the formula, doesn't matter, you can leave it at this stage. Okay, now remember here, since it was a second order differential equation, you have two arbitrary constants k and c making its appearance in your general solution. Okay, so this is yet another problem which can be solved by converting the differential equation to reducible to variable separable form. All right, so let's have another problem on reducible to variable separable form. Again, please pause the video and try it out yourself. All right, so hope you have given it an honest try. Now here, basically we are going to solve this substitution, solve this question by using a substitution which is called the polar coordinate substitution. So we all know that in terms of polar coordinates, we can write x as r cos theta and y as r sin theta. That means we all know that x square plus y square is actually equal to r square, right? And y by x is actually tan of theta. Okay, so you are going to make use of this substitution in order to solve this differential equation. Okay, now there are a couple of terms which actually hint towards making use of this substitution, because many people ask, how do you know that you have to make use of the polar coordinate substitutions in order to solve this differential equation? See, the terms like x square plus y square is appearing over here, right? If you take a minus sign common, it is appearing over here as well, correct? And these terms can also be easily obtained in terms of dr and d theta. Now remember here, one mistake which people make here is that they think that r is constant and only theta is variable. No, that's not the case. Both r and theta are variable. Let me write it down in case you forget here. R and theta both are variables here. Okay. Okay. Now, how will this substitution help us to simplify this problem to a variable separable form? Let's check into that. First of all, from this step, let me differentiate both sides. So when you differentiate both sides, it becomes 2x dx, 2y dy is equal to 2r dr. Okay. Remember, I'm not differentiating with respect to any particular variable. So I'm doing a differentiable with respect to whatever variable is present there. Okay, so if you drop the factor of 2, you can see that x dx plus y dy becomes rdr. Correct. So here the numerator term is clearly your rdr term. So let me just keep this for our reference. Now what about x dy minus y dx? That is pretty easy. Now try to differentiate this term. Okay, so let us differentiate this term. So when you differentiate this term, you end up getting x dy minus y dx by x square is equal to secant square theta d theta. Correct. So from here I can say x dy minus y dx is equal to x square secant square theta d theta. Now we already know that x is r cos theta from here. Okay, from here we can say x is r cos theta. So if I make that substitution over here, it becomes r square cos square theta sec square theta d theta. Thereby these two terms can cancel themselves out, giving you r square d theta. So this is my second important piece of information. That is, my denominator of the left hand side could be written as r square d theta. Okay. Right hand side is pretty obvious. So wherever you see x square plus y square, you substitute an r square for it. So overall, making the substitution into my differential equation, I will end up getting r dr divided by r square d theta is equal to under root of 1 minus r square by r square. Correct? I can clearly cancel off. Let me first simplify this. I can clearly cancel off r from the numerator over here. Not only that, there will be an r appearing in the denominator of the right hand side also. So this r and this r will also get cancelled. Okay. Having done that, it's a clear-cut case of variable separable. So you can write dr by under root of a square minus r square is equal to d of theta. Correct? Let's integrate now both sides, having separated the variables out. This is going to be sine inverse of r by a. This is going to be theta plus c. Now remember, we cannot leave our answer in terms of theta and r because that is the substitution that we have made from our end. So we need to get rid of that as well. So from here, first of all, I can say my r is equal to a sine of theta plus a constant, right? R is nothing but under root of x square plus y square, and theta is nothing but tan inverse of y by x. So this is what I'm going to substitute back. So this is my final solution or the family of curves which is going to satisfy this differential equation. So one thing we learned more over here is that we should never shy away from making such substitutions which are basically based out of polar coordinates. So whenever you see terms like x square plus y square appearing, please also consider that there could be a polar substitution that could help you in solving the question. All right, now we'll make a move towards another type of differential equation which we call as the homogeneous differential equation. The homogeneous differential equation. Okay, I'll refer this by the short form HDE. Okay, now before we talk about homogeneous differential equation, let me first talk about homogeneous functions. Okay, so a function f x comma y is said to be a homogeneous function. A homogeneous function of degree n is said to be a homogeneous function of degree n if for any real number t, if for any t where t belongs to real number, f of tx comma ty results into t to the power n fx comma y. Now don't be scared by these mathematical expressions. It just means to say that this function has the degree of the variables or the power of the variables consistently the same throughout the expression. That's why it is homogeneous in nature. If I say an example of a homogeneous function of degree 2, okay, so if I say a function which is homogeneous of degree 2, this can be an example for it. because you can see the variables have been, both the variables have been subjected to the power of 2. Okay, you can also have a term like xy appearing, doesn't make a difference. Okay, so here the power is 1 1, so which adds up to 2. So uniformly the power of the variables, right, either add up to give you 2 or they are individually 2. Okay, so if I give, this is a homogeneous function of degree 2, right? Another function, let's take like this, x cubed plus 3x square y. This is a homogeneous function of degree 3. As you can see throughout the expression, the power of the variables remain a 3, x cubed, and this is 3 is actually a constant, so its power is considered to be 0. Okay, so 3 x2 y1, so 2 plus 1 will become a 3. Okay, now this is what this particular expression is also saying. So if there is a third degree homogeneous function, if you replace your x with tx and y with ty, for example in this case, if I replace my x with tx and y with ty, here also you'll make the same substitution, you'll end up realizing that t cube can be pulled out common, leaving behind fx comma y expression back. So this is t cube fx comma y. Okay, so whenever an expression satisfies such kind of a relation, we can say that it's a homogeneous function of degree 3. So in general, if it is a homogeneous function of degree n, it will seem to satisfy this particular condition. Now, what is a homogeneous differential equation? Any differential equation of the nature dy by dx is equal to fx comma y by gx comma y, where f and g both are homogeneous function of the same degree. So these two are both homogeneous functions. These two should be both homogeneous functions of the same degree. This is very important, of the same degree. That means overall this is a homogeneous function itself of degree 0. That means whatever degree is on top, the same degree is on the bottom. Okay, a typical example could be something like this: dy by dx is equal to xy plus y square divided by x square. So as you can see, your numerator is a homogeneous function of degree 2. So this is a homogeneous function of degree 2. Denominator is also a homogeneous function of degree 2. So this is an example where you can call this differential equation as a differential equation which is homogeneous in nature. Okay, now how do we actually solve such kind of differential equations? Very simple. The idea is to convert such kind of differential equations as, let's say, a function of y by x or x by y. Okay, it depends upon your call, because whenever you have dx by dy, we prefer converting it to something like, let's say, hx by y form. Okay, how do you do that? Very simple. For example, if you want to convert this as a function of, you want to convert this differential equation as this format, all you need to do is divide both sides by x square. So when you divide both sides by x square in the numerator and denominator, you end up getting y by x plus y by x the whole square by x square, which is actually 1. Okay, now what do I do after this? We normally make, in this case, we make use of the substitution y is equal to vx and try to proceed with the problem to convert it to a variable separable form. In such case, we make the substitution x is equal to vy, right, and try to again convert this expression into a variable separable form. Let me show you on an example. All right, so here you can see a question. The question says, show that the given differential equation is homogeneous and solve it. Okay, so the question is x square plus xy dy is equal to x square plus y square dx. Okay, so if you write it as dy by dx expression, you will end up getting x square plus y square by x square plus xy. Now this is of course a homogeneous differential equation because dy by dx has been expressed as the ratio of two such functions which are homogeneous in themselves and both are of the same degree, right? This is homogeneous of degree 2. This is also homogeneous of degree 2. So it's a ratio of two homogeneous functions of the same degree. So this makes this differential equation as a homogeneous differential equation. Now, what do we do in this case? You can directly make use of the substitution, right? Many people, they convert it to as a function of y by x, but you can directly substitute y is equal to vx right in the present form. But remember to do following things. V is also a variable just like your x and y. So whenever you are writing dy by dx, many people, they make a mistake that they start treating their constant v as a constant. Please let me tell you, v is not a constant. So v is a variable here in this case, just like your y and x are. So when you're finding dy by dx, you have to apply product rule over here. So it becomes v plus x dv by dx. Okay. Please remember this result because you'll be using this very commonly while solving homogeneous differential equation. Now, so dy by dx would be replaced with v plus x dv by dx. Okay. On the right hand side, x square will remain an x square, but y square will become a v square x square. Denominator also x square. xy will become x vx. As you can see, you can cancel out x square from both numerator and denominator. That will leave you only with 1 plus v square by 1 minus v. Okay. Now let's take the v on the other side. So x dv by dx is 1 plus v square by 1 plus v minus v. Okay. If you simplify this, it will become 1 plus v square minus v square by 1 plus v. V square gets cancelled. We have 1 minus v by 1 plus v. So ultimately, the desired expression or the desired differential equation has now arrived. Okay, that's the variable separable form. We can easily write it as 1 plus b by 1 minus v dv is equal to dx by x. So the variables have been conveniently separated, and now we can integrate both the sides. Okay, how do we integrate this? Very simple. We can generate this denominator term on top. So we can write this as minus of 1 minus v. Okay, remember when you're doing that, you already have created v minus 1 on top. So we have to add a 2 here. Okay, again, I'm just using my skills of indefinite integrals, nothing else. Right? Okay, no issue with this. Fine. So now let's split these terms as negative 1 dv. Okay, negative, you can say send the negative on the other side also in order to make your life simple. So 1 dv plus 2 by 1 minus 1 dv is equal to negative dx by x. Okay. Oh, 1 second. I think when we wrote a v minus 1, we cannot take this negative out like this. 1 second. Just a small mistake has happened. So this is nothing but minus 2 with a negative sign. Yeah, now it's correct. Right? So now you can make this change. You can take this as plus 2 and a negative 1 over here. Negative 1 over here. Okay. Now this is quite simple to integrate. So it just becomes minus v and minus 2 ln mod 1 minus v is equal to ln x. Now the constant of integration can also be written in terms of log itself. So you can say ln c over here. Okay. Now I can club up terms. So you can say v is equal to minus 2 ln 1 minus v minus ln x and minus ln c. Okay. So you can further simplify this. V is equal to c. In fact, all are negatives. So you can say negative negative ln 1 minus v the whole square into cx. Correct? Yeah. So e to the power minus v is equal to cx 1 minus v the whole square. You can substitute your v back now in terms of y by x. So this becomes cx 1 minus y by x the whole square. Okay. Now this is subject to further simplification that depends upon the option provided to you in the question. So meanwhile, you can end this process over here. So this becomes your family of curves or solution or general solution to be more specific for this homogeneous differential equation. So now I'm sure this is an NCERT problem, by the way. Now I'm sure through this example, the process is basically set up. How do we deal with a homogeneous differential equation and how do we identify a homogeneous differential equation more importantly? Now let's look into another problem. I would request you all to pause the video right now and try it out yourself. So hope you have given an honest try to this. Now in this question, first of all, we need to be sure that we are dealing with a homogeneous differential equation. Now how do we deal with that? Very simple. So if you write this in terms of dx by dy or dy by dx, now many people ask, we can also write it as dx by dy or dy by dx. How are we sure about it? Okay, which form to write it in? How are we sure about it? See, we see a term x by y appearing in our expression. So there's an x by y here, there's an x by y here, x by y here, etc. So it is convenient to write it as dx by dy because then we can make the substitution of x is equal to vy. Getting my point? So here if I write dx by dy, so we write it as e to the power x by y minus 1 divided by 1 plus e to the power x by y. Okay. So we can here say conveniently that these all terms are of 0 degree, right? This entire term in combination is a 0 degree term. Okay. So this itself is a function. Now we can actually check it out also. So if you call this function as x comma y and try to replace your x with tx and y with ty, you see that there is no effect on this function. So it will be something like this, which is nothing but e to the power x by y into x by y minus 1, right? It is as good as saying t to the power 0 f x comma y. So this term is a homogeneous function of degree 0. And so is this term. This term is also a homogeneous function of degree 0. So overall, this differential equation is also a homogeneous differential equation, right? You can make this quick check, right? Not take you much time. Now what we are going to do is, since x by y has been present everywhere, I can write my x as vy. Okay. So if you are willing to write y as vx, it will lead to terms which are very difficult to integrate. So my suggestion is be observant that whether x equal to vy will make my life simple or y is equal to vx will make my life simple. In this case, it's obviously that x is equal to vy is going to make my life simple. So here x is equal to vy, so dx by dy you can write it as v plus y dv by dy. Make sure you are using product rule carefully here. So your left hand side, which is dx by dy, will now convert to this expression. Right hand side will become e to the power v minus 1 by 1 plus e to the power v. All right. Let's take this v on the other side. So y dv by dy is equal to e to the power v minus 1 by 1 plus e to the power v minus v, which is nothing but e to the power v into v minus e to the power v minus v minus v e to the power v by 1 plus e to the power v. This term and this term will stand cancelled. Okay. Now I think we can make use of the variable separable 1 plus e to the power v divided by we can say v plus e to the power v is equal to minus dy by y. Is that fine? Hope I have not missed out any term anywhere, right? In case I have missed out any term, please point it out in the comment section of this video. Fine. So once we have made this, we are now free to integrate both the sides. Now both integrations are quite simple because if you see your left hand side, the derivative of this expression is actually your numerator, isn't it? So if you take 1 plus e to the power v as your t, then 1 plus e to the power v dv is your dt. Okay, so this is like integrating dt by t, and same type of integration is on your right hand side as well. Okay, so this answer becomes very simple. ln t means ln v plus e to the power v is equal to negative ln y. Since everywhere is ln, we can put ln c in place of our c, right? So ln v plus e to the power v is equal to ln c by y. Get rid of ln terms from both the sides, and v is nothing but x by y. So x by y plus e to the power x by y is equal to c by y. If you want, you can multiply with y throughout also and make it further more simplified. So this expression will become x plus y e to the power x by y is equal to c. Right? So this makes our final answer. This is our answer to this particular differential equation. Okay. So please be careful. This problem was basically chosen because you should be aware when to use y is equal to vx substitution and when to use x is equal to vy substitution. Now, there are certain types of homogeneous equations which are actually not directly represented as a homogeneous differential equation, but with the use of certain substitutions, you can actually convert it to a homogeneous differential equation. That is what we classify under reducible to homogeneous differential equation forms. Okay, let me explain this through a simple example. Let's say we have this question. Now, right now in the present form, it doesn't look like to be a homogeneous differential equation, right? But wait a minute, we can actually convert it to one. How? Let's check it out. Here I can write my denominator, which is sine 2y minus x cos y, as 2 sine y cos y minus x cos y. Okay, take the cos y terms from the denominator to your left hand side. So you can write it as cos y dy by dx is equal to sine y plus x by 2 sine y minus x. Okay, now the presence of cos y dy by dx term indicates that you can actually make a substitution. Sine y is equal to vx, right? Now this actually surprises most of us. You'll get to know all these substitutions only through a very careful scrutiny of the problem. Okay, so if you differentiate both the sides, you get cos y dy by dx is equal to v plus x dv by dx. So your left hand side is already present as this term, so you can make that substitution as v plus x dv by dx on the left hand side. Right hand side, it becomes vx plus x by 2 vx minus x. X can be removed from both numerator and denominator, giving you this expression. Take the v on the right hand side, so x dv by dx becomes v plus 1 by 2v minus 1 minus v. I think if you simplify this, it is going to give you 2v minus 1, v plus 1 minus 2v square plus v. Okay, that's nothing but 1 minus 2v square plus 2v by 2v minus 1. Okay, hereafter you know what to do. It's a case of variable separable. So 2v minus 1 by 1 minus 2v square plus 2v dv is equal to dx by x. Okay, perfect ground for us to now start integration on both the sides. While the right hand side integral is simple, for the left hand side you just have to make a minus substitution. 1 minus 2v square plus 2v as t. So minus 4v plus 2 dv will be nothing but your dt. So if you take a minus 2 common, so 2v minus 1 dv is nothing but your dt. So your numerator term here could be written as negative half dt by t. and right hand side remains dx by x, right? That's quite simple. Now, completing the integration process over here, it becomes minus half ln t is equal to ln x plus ln c. That is ln 1 by root t is equal to ln cx. Drop the ln from both the sides. So 1 by, or you can say a root of t. Let me just flip the points here. Root t is equal to 1 by cx, right? What is root t? Root of 1 minus 2v square. Now what is v here? Remember you had substituted sine y is equal to vx. So v is nothing but sine y by x. So you can directly make that substitution here. Plus 2 sine y by x is equal to 1 by cx. Okay, you can square both the sides. You can simplify terms by multiplying throughout with x square. So okay, let me do that for you. So it's nothing but 1 plus 2 sine square y by x square plus 2 sine y by x is equal to 1 by c square x square. Multiply throughout with x square, it becomes 2 sine square y plus 2x sine y is equal to 1 by c square. See, 1 by c square is also a constant of integration. Okay, so you can put a c for it. No need to just continue with the same form. So this becomes your final answer or the solution to this differential equation. So as you can see here in this problem, my critical step was actually making use of this substitution. So that's why initially it was not a homogeneous differential equation, but with the use of this, I converted it to a homogeneous differential equation and then followed my regular steps. All right, so let's look into this problem. So let's pause this for some time and try it ourselves. All right, so let's look into this question. The equation of the curve passing through 1, 0 and satisfying this differential equation is given by which of the following options, right? Now here you have been given a complicated looking differential equation. So what we'll do first we'll expand it. So when you expand it, it becomes y square dy by dx the whole square plus 4x square plus 4xy dy by dx, and on the right hand side we'll end up getting a y square dy by dx the whole square plus y square plus 2x square plus 2x square dy by dx the whole square. Okay, so this and this term will get cancelled off, and if you collate the terms together you end up getting 2x square dy by dx the whole square. We end up getting minus 4xy dy by dx, and the rest of the terms are y square minus 2x square equal to 0, right? Now treating our dy by dx to be let's say a variable p, we actually see that it's a quadratic equation in p, correct? So let us apply Sridhar-Acharya formula or the quadratic equation formula, what we call it, to solve for p. So p will be minus b plus minus under root b square minus 4 a c by 2a by 2a, correct? Let's take the factor of 4 and remove it from everywhere and simultaneously divide by x square also. So outside will give you y by x, whereas inside it will give you this will enter as 16x square y square, so it will get cancelled off with this will giving you x plus y the whole square. Okay, Here it will give you minus y by x the whole square minus 2 into 2. In fact, it will become 16, so it will become a half over here. Right? So further simplifying this, it will give me the value of p, which is nothing but dy by dx. Let me start using dy by dx for p. That will be y by x plus minus under root. Simplification of this will give you half y by x the whole square plus a 1. Okay. Now, we can conveniently claim that this is a homogeneous differential equation, right? And once you have ensured that, we can use the process that we had learned for solving a homogeneous differential equation. Since y by x is appearing everywhere, it's convenient to assume y is equal to vx, and also there is a dy by dx term over here. Okay, so dy by dx is nothing but v plus x dv by dx. So making this replacement over here, you end up getting v plus x dv by dx is equal to v plus minus under root half v square plus 1. Okay, v and v will get cancelled off. Okay, giving you x dv by dx is equal to under root of v square by 2 plus 1. Okay, of course a plus minus. Of course a plus minus term will come. Okay. So let us try to separate the variables out over here. So this will become dv by under root of 1 plus v square by 2 is equal to plus minus dx by x. So this will give you, this is actually nothing but v by root 2 the whole square. You can consider this to be v by root 2 the whole square. So this will give you ln of v by root 2 plus under root of v square by 2 divided by 1 by root 2. So root 2 will come outside like this. So plus minus ln x plus an ln c you can put. Right? So you can put it as plus minus ln cx. Okay, root 2. In fact, you can put your v back as y by x over here. So you have a minus root 2. So you'll have y plus under root y square plus 2x square. Okay, that's fine. Well, let's simplify this even further. By the way, if you see this term, it'll give you a root 2 ln y plus under root of y square plus 2x square. Okay, and root 2 ln root 2, if you take on the other side, it could be observed under c only. So you don't have to explicitly show that term ln root 2, because you can observe that under ln c term. Okay, now in order to get the value of c, we have to use the boundary condition provided to us in the question. So let's go back to the question. The question says the curve passes through 1, 0. That means when x is 1, y is 0. So let's put that here. When x is 1, y is 0, that will give you 0 plus under root 2 is equal to plus minus under root c. Okay, so I can say c is nothing but root 2 to the power of root 2. Okay, in fact, you can say plus minus there also. So if you have a minus, it will become minus 1 by root 2. Let me just account for that here. So this is nothing but c is equal to root 2 to the power plus minus root 2. Right? Okay. So now, giving a final shape to our answer here, this expression could be written finally as root 2. In fact, you can get rid of now the ln terms from everywhere. So I can write this as ln this equal to plus minus 1 by root 2 ln 2 root 2 x, right? Okay, so this is y plus under root. In fact, I have missed out an x down here. Okay, there will be an x term also here. Yeah, so y square plus 2x square by x is equal to, you can say, a root 2 x plus minus 1 by root 2. Is that fine? Let me check whether any of the options matches with this. Yes, option A is the one which is exactly matching to this. Okay, so as you can see, the main important point to be noted here is that you have to convert this to a homogeneous differential equation. Okay, by converting it first into a quadratic in terms of dy by dx, solving the quadratic by using the Sridhar-Acharya formula, and then once you do that, you realize you end up getting a 0-degree homogeneous equation on the right hand side of dy by dx. And thereafter, you know the process. You have to substitute y is equal to vx and thereby convert it to a variable separable form, and then seal off the problem as we normally do it by using our indefinite integer. Okay,